This is the lecture for Tuesday, October 2nd. I'm re-recording this lecture. During class today, I was not able to record the lecture due to a broken cable. I've now fixed that cable, and so I wanted to record this lecture so that you have a complete archive of the lectures while you're studying for the final exam and such. So I'm just going to cover over the new material that we covered in class again. So we talked about friction. Friction is resistance to motion due to roughness of the surface. So for example, if I have some object here, it does not move unless I push it with enough force to make it move, right? And that resistance to the sliding of the object is friction. The word static is referring to not moving or stuck. The word kinetic refers to moving in the case where we have something that's sliding along. So first let's consider an object on a table, a stationary object on a table. If we do a close-up of the surface between the object and the table surface, then we see there's roughness in the object and in the table surface. Now, and that's the cause of friction, why it's difficult to slide things along the surface. If we don't pull hard enough or push hard enough, the object will not move at all. And this is because of the force of static friction. So remember, static means not moving. And we call this static friction force Fs. S for static. Now suppose I pull with a force capital F horizontally on this object sitting on the table or some surface, but let's say you don't pull hard enough and it does not move. Then what's happening is that there's this force of static friction that's opposing your force. Let's say this direction you're pulling is in the plus x direction. Now, since it doesn't move, the net force component in the horizontal direction must be 0. And so the net force x component is F minus Fs, which is equal to 0, and so Fs is equal to capital F. It's counteracting your force exactly. Now let's consider this in more detail. Let's talk about all the forces on the object, including the vertical forces. If I include the vertical forces, then I have force F that I'm pulling, the force of static friction. There's a normal force, Fn, that the table pushes up on the object, and then there's the force of gravity pulling the object down. If we pull hard enough, then the object will start to move. So there is a limit to how big this static friction force can be. We call the maximum amount of static friction force Fs maximum. Fs maximum, the maximum static friction force. If we pull with a force F that exceeds this maximum value, so if F is greater than Fs maximum, then the object will start to slide. It turns out that this maximum value of the static friction force is proportional to this normal force. Okay, this is an empirical observation. The more normal force you have, the more friction you have. You can think of it as follows. If I have this very light eraser, the normal force is just enough to balance the weight of the eraser, and it's rather easy to move. However, suppose somebody else is pressing down on the eraser, then it's much harder for me to move it along because friction is much stronger, a static friction force. So it turns out that Fs maximum is proportional to the normal force Fm. So let us define the coefficient of static friction. So this is not a force, it's a ratio of forces. The coefficient of static friction, it's mu of s. That's the Greek letter mu, small Greek letter mu sub s. Okay, that is the ratio of the maximum static friction force we just discussed to the normal force. It has no dimensions, it's just a ratio of two forces. There's no units. So if I cross multiply, then the maximum force of static friction is mu s times Fn. This is the way you probably will be using this coefficient of friction, static friction, most of the time. So if we pull with a force F that exceeds mu s Fn, which is this product is equal to the maximum static friction force, then the object will slide. So if you pull with a force greater than mu s times the normal force, then the object will slide. Now, once the object is sliding, we call the force of friction kinetic friction. And in general, once an object is sliding, the amount of force that the friction exerts will be less than the maximum static friction force. This has to do with the fact that we were talking about the surface roughness is causing the force of friction. You can think about the molecules between the surface of the object and the table as bonding together. And with static friction, it's these bonds that prevent the motion, the sliding motion. But eventually you break the bonds. You push it hard enough or you pull it hard enough so that these bonds are broken and it starts to slide. But still there's some resistance to sliding as it's moving along, and that's kinetic friction. So once the object is already sliding, the force of friction is what's called kinetic friction, Fk, F sub k, where k is for kinetic, the force of kinetic friction. The force of kinetic friction is also proportional to the normal force, Fn. Okay. And so we can define what's called the coefficient of kinetic friction, mu k. That's again with the Greek letter small mu. It's the ratio of the kinetic friction force to the normal force. And most of the times you'll be using Fk is equal to mu k times Fn. In general, the force of kinetic friction will be smaller than this maximum static friction force, and so mu k will be less than mu s. This is simply the fact that when the object is stationary, there's these bonds between the surface of the object and the object and the table underneath it. But once you break the bonds, there's still some resistance, but it's not as much as it was when they were stationary. Okay, so a comment about the direction of the friction force. The friction forces always point in the direction opposing any motion. I mentioned the analogy in class that friction is sort of like your friend that always wants to do the opposite of what you want to do. You pull in one direction, friction is pulling in the other direction. It's trying to prevent the motion from happening. Okay. So for static friction, Fs points in the direction needed for the net force to be 0. You pull in one direction, it pulls in the other direction so that the net force is 0, nothing moves, thereby preventing any motion. Now, for kinetic friction, Fs points opposite to the direction of sliding motion. It tries to slow down the sliding object. So for example, if I'm pressing this eraser in this direction, I'm going in this pushing in this direction, friction is trying to slow down the sliding motion, so it's opposing that motion. Similarly, for the static friction case, I'm pressing against this eraser, but it's not moving. So I'm pressing in this direction. There's a friction force there's a force of static friction opposing exactly my force that I'm pressing. Let's now consider an example. Let's suppose I have a block with mass m that sits on an inclined plane with angle 15 degrees. If the block doesn't move, what is the smallest possible value for mu s? Okay, so if you're faced with a problem, what is the smallest possible value for mu s? What that means is that if mu s were smaller, the block would slide. Okay, that's logically equivalent. If mu s were smaller, the block would slide. This is equivalent to saying that the force of static friction is equal to the maximum value that it can have. Because if it were not equal to the maximum but less than the maximum, then I could make mu s a bit smaller, and this could be made a bit smaller. Okay? So that's what we're looking for. We're looking for setting Fs is equal to Fs maximum. So now let's analyze the problem. So if you're not familiar with inclined planes, take a look at the supplement from Thursday's lecture, the one called Applying Newton's Laws. So let's say so we're given this angle 15 degrees. I'm going to draw first the perpendicular to the inclined plane surface, Fn, the normal force. Then we have the force of static friction going in this direction. The reason it's going in that direction, it's preventing the block just from sliding down the plane. Remember, this block is not jumping off the surface, so there's no net force in this direction. There's also no, because the block just is not moving in the plane either, the net force in this parallel direction is also 0. Now, the force of gravity points straight down, and again, in Thursday's lecture, the supplements called Applying Newton's Laws, I said that you can take this vertical force from gravity and to get components of this force. So there's a component here, and that will be, I get an Fg sine of 15. It's going down the plane. Then I have this component here, and that's Fg cosine of 15, and that's also going in the negative direction. I'm taking off the plane perpendicular, so this is the symbol for perpendicular. I take that to be positive. I take up the plane parallel, that's a symbol for parallel. This will be my positive parallel direction. So now let's analyze what's going on in the direction perpendicular to the surface. We have the net force in the perpendicular direction is 0 because it's not lifting off the plane, not lifting off the plane. Okay, this will pretty much always be true. We will not consider problems where the block is jumping off the plane. All right, so then we have Fn in the positive perpendicular direction, and then we have this little piece going in the negative perpendicular direction, Fg times the cosine of 15. And so since Fg is equal to mg, I have mg cosine 15. And we said this is equal to 0, so Fn must be equal to mg cosine 15. Okay, next we're going to look parallel to the surface. So if we're parallel to the surface, then let's take a look at what we have here. Parallel to the surface, we have the force of static friction is going up the plane, so we have Fs, and then we have this component is parallel to the surface, and that's going in the negative parallel direction, so I have minus Fg sine of 15. Okay, the sum of the parallel forces should be equal to 0 because there's no motion at all in the parallel direction. And so we have Fs is equal to Fg sine of 15, or m times g times sine of 15. Okay, so now we use the fact that the smallest possible µs means that the static friction force has reached its maximum value. If µs were any smaller, then the block would slide down the plane. Okay, so it's just about to slip. It's about to start sliding. So we know that Fs maximum must be equal to Fs. We calculate that Fs is mg sine of 15. But we have also the formula, the definition that Fs maximum is µs times Fn. Okay, so that's nice because we want to solve for µs. And so Fn we've solved for up here, mg cosine of 15. So we get µs times Fn, which is mg cosine of 15. So now we have this equation for Fs maximum and this equation for Fs maximum. We set them equal to each other. Mg sine of 15 is equal to µs mg cosine of 15. The mg's will cancel out. So I'll get µs is equal to sine of 15 over cosine of 15, or the tangent of 15. And it comes out to 0.268. All right, the next topic we'll talk about is drag forces, or air resistance. So we're going to consider a baseball moving with some velocity, and there's airflow that goes around the baseball that actually slows it down as it's going. Okay. So the drag force will point in this direction here, exactly opposite to the velocity vector. So if it's moving this way, the drag force tries to oppose the direction of motion, just like friction we talked about. So as you could guess, the drag force is proportional to some quantity. So I'm going to write down the formula, but I'm trying to motivate some of the things in the formula. The bigger the baseball is in area, the more air it has to push out of the way, so that gives more drag force. So it's proportional to the cross-sectional area, how big of the object it is as seen by the air that's flowing past it. So for a ball of radius capital R, the cross-sectional area A is pi r squared. Now, this next step is not obvious, but turns out if the object is going rather fast, then the drag force is proportional to the square of the object's speed. For slow objects, it's proportional to the speed, but for fast objects, it turns out to be proportional to v squared. It's related to the fact that kinetic energy is also proportional to v squared, but that's something we'll do later. Okay, this dependence on speed squared is true for objects traveling quickly through the fluid. So we're using the term fluid to talk about either air or water, and these formulas apply in those cases. Okay, so then it should also be proportional to the density of the fluid, which we call rho, this Greek letter rho, small Greek letter rho. And the density is the mass per unit volume. So density rho is the mass of the fluid divided by the total volume of the fluid. And it has units of kilograms per meters cubed. All right, so it turns out if you take these quantities, the area, the cross-sectional area, the speed squared, and the density, multiply them together, AV squared rho, and you work out the units m squared, m over s squared, meters over second squared, kilograms per cubic meter, you end up with kilogram meters per second squared, or newtons. So this is actually a way of guessing the formula for the drag force. The actual formula, as we'll write it down, is that the drag force is equal to 1/2, and this 1/2 is just the convention of how to define it. 1/2 times c, the drag coefficient, so that's a unitless object, which is some number like 0.2 or 0.7. And rho is the density of the fluid, and A is cross-sectional area, and v squared is the speed squared. So that's the formula, that the drag force is 1/2 the drag coefficient, rho, the density times the area times the speed squared. So let's try this with an example. So there's this concept of terminal velocity. If you're falling down, so you fall, very unfortunately, you fall down and you get faster and faster eventually. However, you're going so fast that the air resistance is enough to compensate and to cancel out your force of gravity, and you don't go any faster. And this is what's called terminal velocity. And it's essentially the maximum speed while falling with air resistance. So let's calculate the terminal velocity for a 75 kilogram man with cross-sectional area of 0.18 square meters. Let's take the drag coefficient of air to be 0.70 and the density of air to be 1.21 kilograms per cubic meter. Okay, so terminal velocity means that the drag force of air resistance cancels out the force of gravity. So terminal meaning the final velocity, you don't get any faster. And so the acceleration in the y direction is 0, so the net force in the y direction is 0, so these things must cancel. So we have that the drag force minus the force of gravity equals to 0, or else the drag force is equal to Fg, which is equal to m times g. Now we can take the formula for the drag force, 1/2 c rho a v squared, and set it equal to m times g. We plug in the values we got. 0.7 for the drag coefficient, 1.21 kilograms per meters cubed for the density. A is 0.18 meters squared, and then we have this unknown speed squared, which we're trying to solve for. The mass is 75 kilograms, and g is 9.8 meters per second squared. All right, so you can punch this into your calculator, and you get v squared is 9,642 meters squared per second squared. Taking the square root gives that v is equal to 98 meters per second.